Now we're going to talk about chemical reactions involving gases. So for gases in reactions, we'll often specify the quantity in terms of its volume at a given temperature and pressure. So in stoichiometry then, instead of using like the molar mass to convert mass to moles, we can use the ideal gas law to find the moles of gases. So the moles would equal the pressure times the volume divided by RT, or if we need to determine the volume at the end, we can use this rearrangement of the ideal gas law. When gases are at STP, it's much simpler because then we can use the molar volume of a gas. So if the problem is talking about this is occurring at STP, you should do a little happy dance because it's going to be a lot easier. When we're talking about pressures here, the pressures could be partial pressures. It'll work the same way. So the general plan here, the path, this is what we normally see, grams to moles to moles to grams. So again, the mole to mole part in the middle is always the same. Now at the beginning we might have pressure, volume, and temperature of a gas. We can use that information to find the moles. From the moles we can find one of those, the pressure, volume, or temperature of the gas. So let's do an example. In the following reaction, 4.58 liters of oxygen was formed at a pressure of 745 millimeters of mercury and a temperature of 308 Kelvin. How many grams of Ag2O decomposed? So we're just going to follow the same pattern we've been using all semester. We're going to highlight the numbers and see, well, what's the question? We want grams of Ag2O. And then I'm going to take these numbers and write them under the balanced chemical equation to just kind of organize things. So 4.58 liters of oxygen. So I'm going to write that under oxygen. Was formed at this pressure. So this is also referring to the oxygen. And this temperature. Again, still referring to the oxygen. Then the question is, how many grams of Ag2O? So there's my question, and the unit I need there is grams. We've got amounts of substances, and we've got a balanced chemical equation, and so this is stoichiometry. So the first thing you should think of is grams to moles to moles to grams. And then we look at what do we actually have. There was a question on a worksheet that a lot of people kind of went nuts on. It gave you moles of one thing and asked you for moles of the other. And instead of just doing the mole to mole, they did moles to grams to grams to moles, which doesn't actually work. I know it's really tempting, but if you just have moles, that just means it's a lot simpler. So the moles are always in the middle. So here, we're not given a mass, we're given a volume, a pressure, and a temperature of a gas. So we're not going to start with mass, we're starting with PVT. And then at the end, we actually do want grams. So there's the path. And again, if you're struggling at all with any of these problems, write out the path first. It really, really does help. So I'm going to use the pressure, volume, and temperature of the gas to find the moles of gas. Now this is not going to fall into my dimensional analysis one long equation, but I'm going to use the ideal gas law to do that. So the first thing is to find the moles of oxygen. So rearranging the ideal gas law, the moles of oxygen is equal to the pressure times the volume divided by R times the temperature. Well, here we have the volume and the pressure and the temperature. Are all of those good units? No. Millimeters of mercury isn't going to work, right? So we need to convert that to atmospheres before we can use it in the ideal gas law. Dang it. Where's my pencil again? So 745 divided by 760 gives me a pressure of 0.98026 atmospheres. So I can find the moles using the pressure and the volume. And the ideal gas constant. And the temperature. And I'm getting 0.17763 moles of oxygen. Anybody else get that? So moles of oxygen, that's moles up here in my path. So I've got moles of oxygen, and now I can continue on my way and calculate moles of Ag2O and then grams of Ag2O. So I got moles of O2 down here and moles of Ag2O down there, so that my units all work out. I need, this mole ratio comes from the balanced chemical equation. 2 moles of Ag2O are going to give me 1 mole of O2. And then how do I convert from moles to grams? Molar mass. So I've got 2 silvers, 107.9. Yeah. Ag2 and an oxygen. So 231.8. So 231.8 grams of Ag2O per mole. And I got 0.17763 times 2 times 231.8. $82.349 grams. So that's going to be 82.3 grams of Ag2O that would be decomposed. Any questions? So let's look at one where we can use the molar volume. This one says how many liters of oxygen at STP, that's nice, are required to form 10.5 grams of water. So 10.5 grams of water, and then the question is liters of oxygen. So I'm going to write 10.5 grams under H2O, and question mark liters under oxygen. So this is stoichiometry, so we should start with grams to moles to moles to grams and see if we need to make any changes. So here we are starting with a mass of water. We can go to moles of water, to moles of oxygen, but then instead of grams, we're going to go to liters. Now, in the previous problem, we used the pressure and the temperature to find this. We would need we'd find the moles, then we'd use the ideal gas law. You can do it that way, but it's longer, right? And what are the temperature and pressure? Well, they're given here, STP. The temperature is 0 Celsius, or 273 Kelvin, and the pressure is 1 atmosphere. But that means that we can use the molar volume of a gas, which tells us that we have 22.4 liters is equal to 1 mole. So we'll start with grams to moles to liters. So we've got 10.5 grams of H2O. And then we're going to go to moles of H2O. And then we're going to go to moles of O2. And then we're going to go to liters of O2. I'm going to take this unit and put it in the denominator, grams of H2O, so those are going to cancel out. Moles of H2O and moles of O2. Get all the units in place, and then they're going to tell me what to do. So in this first one, I need the molar mass of water. So we can calculate that, but I'm just going to save some time because I happen to remember that one. Then the mole ratio here, coefficients in the balanced chemical equation. So 1 mole of oxygen for every 2 moles of water. And then this last one, that's where we can use 22.4 liters per mole. You can only use that at STP and only for gases. It's not true for anything else. So $10.5 divided by 18.016 divided by 2 times 22.4, 6.5275 liters. As with most of our problems, we've got 3 significant figures going on here. So I'm going to round this. I've got a 2, and the next number is 5 or larger, so this is going to round up to 6.53 liters of oxygen. Any questions?